Hello everyone, this is part 2 of series Scientific 3D Image Analysis in Python. This is Arash, and in this session we're going to talk about a few image processing pipelines such as cleaning the images, filtering them, and thresholding them. So these are a few important operations that we could do on scientific 3D images that we are going to make ourselves familiar in this part. Okay, let's begin with talking about why actually we do need to do this cleaning stuff, right? So because these images, these are being captured using some scientific devices that might have some noises built into them because of the processes that are involved in capturing those data. It is always inevitable to have some random noises here and there because of the quality of the images, or because the thing that we are trying to capture is very actually difficult to capture. So these the devices, they usually work at the boundaries of accuracies that they have, and it causes significant image quality reduction, right? So because if we are capturing an image from a very small object, we are trying to make it as much as accurate, right? Or if it's a large object, we are trying to capture as much as voxels that we can, or we are trying to increase the field of view. So it is always a battle between the image quality and the speed of the device that takes the images, and it is always a little bit of sacrifice that is being made on the image quality. So knowing how to clean and filter the data is very important. Sometimes people do that manually, but you could also write a code for it in Python, right? Which is a kind of a better way to deal with it, because then you're going to make it very systematic instead of doing it just subjectively, right? Because these images, as I said, these scientific images, every pixel, it has specific meaning. So we do not want to just subjectively play with the intensity of these pixels, right? So let's start by going through different things that we are going to cover. So first we're going to talk a little bit about noise reduction. What are different techniques? We're going to talk about some basic and famous techniques and some more advanced or unconventional techniques, and keep in mind that these filterings are being done in 3 dimensions, so it's a little bit different from 2D filtering, both in terms of amount of computations it needs and the availability of algorithms. So many filtering methods, they have been developed initially for 2 dimensions, but not all of them could be applied in 3 dimensions, right? Or at least there are not like a straightforward packages and you need to write down your own code to do so. So that's quite a space for improvement. And then we're going to talk about how we can change different things about the image, like changing its brightness, its contrast. Again, this is 3D images. And then we're going to talk about a few thresholding methods, which are going to give us a binary image instead of having a grayscale image, right? That is also something that could come very handy in some occasions. And then at the end, we are looking at some of these images, doing visualization and then saving the data, right? Okay. Perfect. So let's start by importing the libraries that we need. I've covered these in the previous part, so I'm not going to talk about these packages that we are going to import. And then simply we need to load or download the data from the link, and then we're going to do a very simple visualization of how the data looks like, right? So we've done this before, so it's quite straightforward. We are taking 3 different slices of this 3D cube and showing it here like XY plane, XZ plane, and YZ plane, right? So these are 3 perpendicular planes that are passing through this geometry. But if you look at these images closely, you could see that there are some sort of a noise built into it, right? Some sort of a white noise, something very, very random going through these images. So for example, if I go from this part of the object to the other part of it, and if I wanted to show that what are the changes in gray intensity, so before entering it, it's a very low value, and then entering it, it's getting higher, like gray value, right? But it's not a straight line. As I go from left to right, you see these are like very small changes, and then when I get outside of the object, getting to the black part, the gray intensity is actually going down, right? So let's call this X, and this is going to be intensity, right? So you see these parts, these are actually noises that we need to get rid of. But the problem is that sometimes when we are trying to flat out this part of the noises, we are going to flat out some of these corners or mess with like the integrity of these lines, right? So that is something that we need to keep in mind to basically the good filter is actually something that gets rid of those noises, but at the same time would not tamper with the integrity of the image and the objects. We don't want the objects to get significantly smaller or larger because they probably have significant meanings to them, right? Perfect. So let's move on with a few noise reduction techniques, right? So two very famous ones. One is a Gaussian filter and the other one is median filter. Gaussian filter, also known as Gaussian blur. Actually, what it does is that if we have an image like this, and you know the image has a space like this, these are different pixels in 2D, right? So for the Gaussian filter, we're going to have a standard deviation as well. So what it does is somehow it takes these samples, the values that it has, and instead of the values that you see, it will put back into the image a distribution that it is fitting over those data points, right? So and basically what it does is that somehow smoothing it out, right? So assume that we have this data point. So the algorithm, it thinks that what's going to be these what can be replaced by basically these pixels that has an average of all of them and a standard deviation of 1, right? So it basically fits a distribution over these data points, and instead of having a very jagged changes between these pixels, it's going to come up with a more smooth transition from one to the next pixel, right? It is good, but it's going to make the image a little bit blurry. So that is the downside of it. So what about the median filter? Actually, a median filter, what it does is that for the median filter, if we have a 3x3 grid, the median filter is that, for example, here we have different gray intensities, right? So something like this. So the median filter is actually takes all these values and it sorts them in a line and then picks the middle one, right, which we call actually a median, and it puts it back here at the center, right? So that is the basic logic of it, and it does that with a kernel size. So it is important that how large we take this window that we are calculating the median for, and that's why the median filter in EndImage actually package is taking something called size, which is actually telling us how big is this filter, right? So a larger the filter size is gonna smooth out the image more significantly. So there is a trade-off between the image quality, getting rid of noises, and getting rid of actual features and patterns in the image. So we need to make sure to do not increase it too much. So usually what it happens is that we sometimes we just do that manually, changing the size to see which image is more appealing to the eye, because as human we somehow understand the concept of these white noises, right? So we probably know that these are not the information we are looking for. We were expecting to see a uniform gray color across this material, because from theory we know that it is a pure material, almost pure, and it doesn't need to have any variations in the gray intensity. So that is how a Gaussian filter basically works, right? And what about the median filter? You see, this is the result that we are getting from the median filter. So if I increase the standard deviation on the Gaussian filter, let's see what is the changes it makes on the image. You see, it's a little bit slow because these are 3D images. So these are all 3D kernels. So that is why it takes so much time, especially if you increase the kernel size, because it needs to reach out for a higher number of pixels every time it makes the inference. You see that the image is getting blurry and blurry, so this comes at the cost of losing some information, but at least what is happening is that here the object is more smooth, right? Okay, you see, you get the idea. And for the median filter we could also do the same, changing the size of the kernel. It's sometimes have the same sort of effect, but you just need to play around with these filters to see which one would fit the data that you have better, actually, right? So a few other filtering methods less conventional, I would say. But it depends. In some occasions, these are actually more useful. So we have mean filter, which is very basic. Instead of calculating the median, what we can do is actually just switch this with mean. So we just take all of these values and put the average of them at the center, right? So this is the target pixel or voxel. But because this is in 3D, it's actually 27 grid, so it's not like 3 by 3. It's 3 to the power of 3. Right, so it's actually, this is the kernel size when we are talking about it, right? So we calculate the average of them and then we put it for the voxel that is located at the center. So what about the other one? So we have maximum filter. It's getting interesting. So you see here 120 is the largest value that we have. So what if instead of putting the average or median, we put the maximum value? What do you think we're gonna see in the images? What effect it's gonna have, right? So it's going to make the filtering bias to the higher values, right? So it's usually makes it would intensify larger values in the image, and larger values associates with brighter colors, right? So what we expect is to see probably brighter colors in the image. So let's run it to check it out. So we have the mean filter, which looks very basic, and here we have the maximum filter. You see, if you can follow up these, for example, some of these white dots that you see in the image, right? So for example, this one, you see here it has grown, right, compared to the bottom one, because the maximum filter actually intensifies, encourages the higher values. It's biased towards them. And then in the contrary, we have the minimum filter, which is actually suppresses the higher values and encourages the lower values. So you see that one has shrunk, and also there is a dilation going on for the black pixels, right? For the darker pixels. So if the proportion of these white to black pixels means something is special in your images, you need to make sure that is this the correct way to go or not, right? So these are also important. So we could also look at this things that are happening in terms of histogram of these images. So if we try to plot the frequency of different intensities, right? You see when we go, for example, from the normal image to the maximum filter, is actually what it does is that it suppresses the lower values, so the distribution would look like something like this, and vice versa. If we go with a minimum filter, it's gonna make the distribution a little bit skewed to the lower values, so it makes a bias towards the lower values, and it changes the frequencies a little bit. The other option that we have is to use a percentile filter. So the code is actually very simple. We're just changing the name of the function: maximum filter, minimum filter, percentile filter, and rank filter, right? So percentile filter, as I said, when we have these images, these voxels, we sort them out in a line from the smaller values to the larger values, right? So they increase in this side. And if we take the middle one, it's called the median, right? But we could stop at every location that we want. So this, if we take this one, it's a maximum filter. We take this one, it's a minimum filter. But if we stop, for example, here is going to be 0.75 percentile, right? So it is somewhere a middle ground between the median and the maximum filter. And same with the rank filter. So with the rank filter, you will count which one out of them you want, right? So a rank 5 means you want the 5th pixel here, which is coincidentally the median one, right? So that is how all these different things work. But the question that a legitimate question is that how should we decide which one is good? Because we are, at this point, we're just a little bit confused. We have too many different filtering methods, and which one is good? How we can justify, if you're doing a research, you're writing a scientific report, how you can justify why you have chosen this specific filter, right? So that is a very valid question to ask. So the way we're going to approach that is actually a very standard approach. We're going to use two metrics. One is called mean squared error, right, which is very famous, and the other one is signal to noise ratio, right? So what do you mean by mean squared error? It means that we can just to understand how good is a filter, We can just compare its difference, its pixel-wise error compared to the original image, right? Because if it makes too much differences, we don't want that, right? We don't want a method that is going to make too much differences in the image. We just want slight differences that help us to get rid of the noise, right? So that is something. So we are looking for low mean square error. And then we have something else called signal to noise ratio, which is actually telling us if we have a signal is just an information. It could be something like this, right? When we go from right to left of an image, the values could change like this. But at the same time, we could have some noises. So these transitions are not smooth when we change the location in the image, right? So you could think about signal to noise ratio is as the height of these large peaks to the height of these small peaks. So what we are looking for is to suppress these small peaks and maintain the large peaks that we see in the image, right? So, and it's measured with the decibel unit because it thinks as these changes in the intensity as some sort of a wave, right? And then we wanted to maximize signal to noise ratio compared to the original image. So we can actually do that by, we have all these images, right? So we could calculate mean square error and signal to noise ratio of them compared to the original image. This is what we are doing here, as you can see, we're calculating MSE of original and filtered images, writing a loop to go through all these different methods that we've done, right? And we could come up with a table actually. It's quite useful to justify our design choices in our scientific method. So you see here we are looking for low mean square and high signal noise ratio. And surprisingly, the median filter, which was one of the basic ones, and it is not very computationally demanding, is giving us the best results, right? So you see, for example, the Gaussian one, that we have increased the standard deviation of it. You see we are getting a very high mean square error, meaning that it is just changing too much compared to the original image, right? And when you see a low signal to noise ratio, it means that we are losing lots of details probably. But this is a trade-off. This is not a very hard rock science of what is a good number. But in comparison, we could say median is doing a good job by maintaining the image integrity and at the same time intensifying the signal itself, right? Okay, perfect. Let's move on to some intensity adjustments. So what we are going to talk about now is that we have these images that some of them could be a little bit dark. So if you are dealing with scientific images, you are probably familiar with this. If you take images and you see that the images look really dark, so you cannot see much in them, for example, they look too much bright, or they look very grayish, so you do not see any details in it. Everything is very gray, right? So this is happening because sometimes the distribution of the data is not actually using the whole available space, right? So if we put here the intensity of the image, and this is the frequency of the values, and we have, for example, with the 8-bit space, we have from 0 to 155 to fill in. A good image is actually getting use of all this space, right? So something like this could be the distribution, and it uses all this space. But sometimes an image would look like this, right? So an image look like this, it means that everything is very bright. So the darkest part that you see in the image is like a mid-gray, right? So we are not using the whole space that we have efficiently. And also it does not come easy to the eye either. So to deal with that, we can do some adjustments on the basically image brightness and contrast. So these are two basic formulas that we could use to change the brightness and contrast. So let's start with brightness. So if we have a distribution like so, we could simply, if we multiply the intensities by a number, we're going to scale it up a little bit, pushing it towards the largest values, right? So that could actually give us a brightness increase. They're not going to be much increase in the darker parts because we are multiplying these positive values. But as we go on, we are going to just create a skewed distribution towards the largest value, right? But at the same time, if b is like smaller than 1, we're going to make it to look like this. So it could go either way to change the brightness. But for contrast, there is a little bit of a different trick that we need to do, is that first we need to move this distribution to be centered at 0, right? And then by multiplying it by a number, we're going to change both tails at the same time. So if we multiply it by a number smaller than 1, we're going to shrink the distribution, make it thinner and or sharper, and then we could go the other way around by multiplying it by a larger number. We could make a more flat and well distributed data, right? So you see, we are bringing it back to the origin, and then after multiplying by changing the contrast, then we are bringing it back to its original place, right? So we could do that with different combinations of them. So you can see here we have different combinations of basically changing different brightness and contrast. So here at the center we have the original image, and as we move to right, we are actually increasing the brightness, decreasing the brightness to the left, and by going down we are actually increasing the contrast. So you see possibly some of the images, this one or this one, these are actually more easy on eye, I would say. You could see more information, and it is basically a better use of all the available image space that we have, right? Okay, perfect. So what's next? So what we can do next is that we could distinguish between different regions of this image based on the color intensity. So thresholding is actually giving us a very simple way to divide this image into white and black pixels, right? Because you see we have some gray values going on as well. So if we wanted to draw a line between two different regions of this image, this could come handy, thresholding, right? Sometimes you have an object in front of a background, and the background is not pitch black, so it's a little bit of a gray going on, and you wanted to get rid of the all background. So thresholding could be a way to go, right? And we have different methods to do that. So we could do Otsu algorithm. We have an adaptive thresholding, and we could go with Yen's algorithm. These are like a few famous approaches that we could use, but there are countless other methods. And the basic of all of them is to minimize the standard deviation in each of the regions themselves, right? So I'm just saying that if I wanted to divide this image into pure black and pure white pixels, where do I need to draw the line, right? So if we look at it from a distribution point of view, because these methods like the classic Otsu is dealing with it as a one-dimensional problem. So we have these, for example, pixels. Let me start again, right? So we have the distributions, this is the intensity, and this is the frequency of them. Here, for example, in this image, you see we have around 20%, I would say, black dark pixels, and the rest are gray and white, right? So if I wanted to represent that, it's going to be a peak like this, and then we have a bigger peak like so to represent the lighter colors, right? So Otsu is actually deciding on where to draw the line in this one-dimensional problem to basically separate the image, and instead of this one, we're just going to have one large peak here and one smaller peak here, right? So it's just dividing the image into just pure black and pure white. But the problem is that where should we draw this line? So the Otsu algorithm just tries to minimize the standard deviation on each of these sides separately, right? So somehow minimizing the summation of these standard deviations, right? Or something like so, like if you look at it from a very generic point of view. So that is the purpose. But there could be sometimes problems with that, because this is a pure one-dimensional problem, and this line could not be valid for all part of the image, right? So if you, in the image, you have a little bit of a gradient going on, for example, assume that in this image, we have darker shades here and lighter shades here because of some artifacts in the imaging, right? In those cases, using one line for all of the image parts is not useful. So what we need to do is to decide about a sliding window, right? That is going to go location by location on the image space. And inside each of these is going to have its own thresholding, right? So it's going to be a locally adaptive thresholding method. And inside each of those blocks, you could use Otsu or any other algorithm, right? But that is the approach when you have a gradient, like the overall color intensity is changing and you don't want it to be affected by that. You need to go with like an adaptive method. So let's have a look at the results that we have, right? So we have, what we are going to use is filters in scikit-image, which is a package that we are using, a Python package. In filters, we have different thresholding methods, right? So we have the yen and we have Otsu, and here we are creating our tiny little local thresholding code, which is actually going, it has a block size and it goes through location by location and it performs the adaptive thresholding, right? So let's have a look at the results. You see this is basically the Otsu thresholding, the first one you see. The second one is the adaptive thresholding, which is very impressive because it seems like it is capturing higher amount of details from the image. It is questionable of if all these details are valid, but still it is interesting to see. So let's compare this one by one. So probably if you look at this section of the image here, right, you see we have a little bit of a tiny structure going on, right? One of these sand particles, it seems like to be broken or something like that. So let's have a look at these images to see how they captured it. Well, nothing going on here. It's basically, there's not much detail going on with the Otsu thresholding. But with the adaptive thresholding, you can see that we are having a little bit of a detail of that particle. Sorry, we need to compare the first images together, right? So we see we're not seeing much details here. But here we have better amount of details of that tiny little structure that we were seeing in the image. And also here, this one, yen, is not bad considering that it is not a local thresholding method. It's performing more or less better. The other thing about this is that you could see that we are seeing some slight spaces inside each of these sand grains. And if you know from theory that it makes sense for your model for your object to have those sort of lower density locations, so it makes sense to go with the adaptive one, right? So this is, again, it's not a perfect science. You need to judge fairly if all those details that you see in the images, they are real. And if they're not, you need to consider like a threshold to get rid of any details beyond a certain level using the filtering methods that we talked about. But combining filtering with thresholding is actually a very good practice. So what I'm curious about to see is that what would happen with these very tiny little spots you see here if we do a median filter before this, right? And that is a good thing for you to do as a practice. Okay, great. So we're just getting close to the end of it by just having a look at a few binary operations, right? So there are a few binary operations that we could do on these images that we have already binarized, right? Which could actually come useful. So if you don't want it to have too many tiny little isolated islands in your image, if it doesn't make sense theoretically, for example, if you have an island, it means that subparticle is hanging mid-air without being connected to anything else. What you can do is to use these useful function in the morphology part of the scikit-image. So one of them is remove small objects, right? So it takes the image and then it takes a minimum size that anything below that it would get rid of it. And the other thing that you could do is filling the image holes. If image holes the image, it doesn't have any physical meaning, you could get rid of it, right? So for example, if I don't know, if it's you're taking an image of something that you know for sure it's solid, it doesn't have any details in it, and you see some variations, it's probably due to noise. So you could just get rid of the small islands or fill the image holes to make your image more clear. So you see here we have cleaned and filled the holes of the image, and it looks much more sharp and clean, right? So but as I said, it all depends on the different things that you're going to do with it. Sometimes those holes actually that we are filling are the actual purpose of this study that you do, right? So, but I'm just introducing different tools that you could use to basically play with the images that you have. So, and at the end, let's do a 3D visualization with Plotly, similar to the previous part that we had. At that time, we were doing the grayscale image, but now you see this is the binary image. The only values we have is zeros and ones, right? So you see how it looks. You could play with it, and then also you could even export this image, take a snapshot, or like reset the camera, or different things that you could do with this. And then at the end, because this is basically could be saved as a TIFF file using TIFF file functionality, you could write this 3D array as a TIFF image. You just make sure to convert it to the right format. So it needs to be, because this is a binary image, it's zeros and ones, it's better to convert it to an 8-bit image for the sake of compatibility with some image viewers here and there, right? That's why we're converting it to 8-bit and then multiplying it by 255 to basically, instead of having 0 and 1, converting it into 0 and 255, right? Okay, perfect. This is the end of part 2. I hope it has been useful, and see you on part 3. Thank you.